Okay, in the last class, we were discussing retiming a loop. We found some problem. When it is just a forward path, we can, we can just introduce delays between every two nodes and bring down the critical path. Then we can get into a node, divide it into maybe two equal halves, again insert a delay between them and so on and so forth. These delays were never part of the original DFG, but we can introduce them from outside and we can bring down the critical path again. Still, till the point it is possible to break down a node into sub nodes. But then when we tried to do the same thing to a loop, then we had a problem. If we started bringing delays from outside, in the end we end up with a negative number of delay. So, feasibility is gone. Okay, that was a problem I discussed at length by showing an example. Now, why does it happen? That is what we will find out today. Why does that happen? What is the problem in retiming a loop? So, consider a loop. In number of nodes, okay, like this: U0 one node, U1 one node. There is a connection. They may have W0 amount of delay between them. U0 can take time T0 microsecond or T0 whatever be the unit. U1 can take T1 unit. Then there may be another node U2 with delay W1. U3 delay W2 ... So, U started with U0 and total n nodes, it should go up to n minus 1. This is U n minus 2. So, this has W n minus 1 delay, this has W n minus 2 delay . So, U n minus 1, after that it comes back to U0. So, together they form, amongst them they form a loop, though it does not mean that there are no other nodes in the DFG. There may be many other nodes around this, maybe U0 can be connected to some of them, some other may be connected to U1, U2 may be connected to some other them, but when you consider them U0 to U n minus 1, among them they form a loop, because you start from U0 and go back, come here, then you finally arrive at the same U0 again. Okay, it is a loop. Each loop, in the loop I have shown the computation time for every node and the delay between every two pair. If you add up all the delays in the loop, that is, if you say W0, W1 ... up to Wn minus 1, that is sigma Wi I equal to 0 to n minus 1, that is the total delay available in the loop. It is called loop delay, total delay in the loop. Similarly, if you add up all the computation times T0 plus T1 plus ... T n minus 1, that is this is called total loop computation time, You can call it TL. Okay. Now, suppose I retime the loop. That means, I will be assigning retiming values to them. So, I will have R of 0 for U0, R of 1 for U2, like that. So, basically I am choosing R of I retiming value for node I. Okay. So, after retiming W0, this delay will turn out to be what? After retiming, it will be original W0 plus retiming value of the destination node for this edge hits at U1. So, destination value is R1, retiming value of the destination node minus retiming value of the source node, source for this edge, I mean this A node, that is R of 0. Okay. Similarly, W1, it will be original W1 plus R of 2 minus R of 1. Okay. Dot dot dot, maybe one more I take, W2 will become W2 plus R of 3 minus R of 2. Dot dot dot, Wn minus 2, it will become Wn minus 2 plus R of n minus 1 minus R of n minus 2, and Wn minus 1, it will become Wn minus 1 original plus R of 0, because U0 is the destination here, minus R of n minus 1. Now, if I add them, these fellows, if I add, I get the total delay in the loop, that is WL, and on this side, that is before retiming, total loop delay is WL. After retiming, these are the delay values, this is the new delay, they are all greater than 0, by the way. The retiming values are chosen such that all are feasible, that is nobody is negative, fine. So, then if I add them after compute, that is after retiming, what is the new loop delay? New loop delay will be summation of the new delays. So, this much is one delay, this much is one delay, like that. Okay. So, if you add them, you see these things cancel. So, you will be left with only this part. So, that is again WL. This is the issue, that when you retime a loop, before retiming loop delay is WL, after retiming also loop delay will be WL. Total delay in the loop cannot increase, you have to just manipulate, so that some delay from some edge is moved forward or backward and like that, but total delay must be same. That is, unlike the forward path pipelining, forward path retiming, you cannot bring additional delays from outside world and insert them in various edges, because total delay in the loop cannot be changed, they remain fixed. I cannot add extra delays from outside. I can move some delay forward or backward by cleverly choosing retiming values of the nodes, only that much can be done. This is a fundamental problem of retiming a loop. Mind you, loop is very essential. For instance, if you have IIR filter, then IIR filter, you have an equation yn which depends on yn minus 1, yn minus 2. That means, there is a feedback from yn through a delay back to the input side. So, that forms a loop. If it is yn minus 2, through 2 delays yn comes back, gets added with the input side and comes to the output. So, that forms a loop. So, loops are very essential. Loops come in various DSP circuits, DSP and communication circuits. Okay. In communication, there is something called decision feedback equalizer, where the output decision about the what symbol was transmitted, that is estimated and then fed back to the processing equalizer for refining some estimate. There is some structure. Okay. So, there is a loop again. Loops occur frequently, and always I tell you, loops are the main cause of problems. Okay. Now, under this then, what best can be done, theoretically at least, what best we can do, what is the minimum value we can bring down the critical path to. Okay. Here, what is the critical path? If every delay is positive, then it will be either the time taken by this node or this node, this node or this node, whoever has the maximum. Okay. Because if they are separated by delays, the 2 times will not be, like T0 and T1 will not get added, because in one cycle U0 does a job, next cycle that is used in U1, and likewise. Otherwise, if you have some delay free paths in the loop, you have to add those node computation times. So, fine. So, there is a loop given with some critical path, some delay distribution, fine. Now, how to adjust the delays, okay, the computations within nodes, so that I can achieve the best possible, that is, I can achieve the minimum possible critical path. We can directly see that we cannot bring down the critical path below that, directly see. What is that? Okay. That is what is my next topic. For that, let us look at this thing. Just if you see the net processing that we are doing, first we are doing a processing by U0, then followed by U1. There is a delay of course, but otherwise processing wise U0, it takes some amount of time T0. Next processing is U1, takes some amount of time T1, then U2, taking some amount of time T2, T3, this is Tn minus 2, sorry I forgot to mention this here, okay, so on and so forth. So, what I do, I first consider a total processor which consists of first U0, then U1, then U2. That is, I am finding out how much is the net job I have to do. So, first I have to start with U0 processing, then U1 processing, then U2 kind of processing, then U3. So, I build up a net super processor, say, okay, which carries on all the jobs. Okay. Then we examine. So, we start with U0. So, suppose this is that job. I am just considering the total job. Delays I will definitely require to, I will be required to insert, but net job, that is maybe U0, then you go to U1, from right to left I am showing U2 dot 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 up to UN minus 1. This is the net job, and how much time it takes? T0 plus T1 plus T2 dot 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 up to T this, that is net time takes is nothing but the loop computation time TL. Okay. Then I take a relook at this job, net job, total job, and instead of having n nodes as before here, like here, U0, U1, U2, what I do, I divide into equal halves, if possible. Hardware may not permit, then I cannot do this optimization. But suppose hardware permits, then I divide them into equal halves. How many equal halves? WL number of, WL is the loop delay, number of equal in terms of time taken, equal halves. Okay. Total time is TL. Suppose the hardware permits to divide the job into exactly WL number of sub jobs, each taking the same time. So, each taking time how much? If they take the same time, total time is TL, WL number of new jobs, new nodes. Okay. So, it will be TL by WL. So, everybody takes TL by WL. Okay, dot 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 dot. Everybody takes TL by WL, TL by WL, TL by WL, dot dot dot, like that. Everybody takes, if it is possible. If it is not possible, I cannot come up to this, but suppose it is possible to look at the total job and divide it equally. Equally means in terms of time, divide it into WL number of sub jobs. Okay. Since they are equal in time, everybody will get a share of TL by WL. Then what I do, I dedicate WL number of nodes. So, this is one node, you can call it U0 prime now, because U0 notation has been used earlier, I cannot here. So, I cannot use the same notation. Then the next job you call U1 prime, next one you call U2 prime, this is the way. First U0 prime, this is U0 prime, then it goes here U1 prime, then it goes here U2 prime. I am showing from right to left, and so on and so forth. Okay. So, U2 prime dot dot dot, total WL. Okay, maybe one more I show, U3 prime, WL is total. So, we started from 0, so it should WL minus 1, then only total is WL. So, I form the loop, the same thing. Okay. U0 prime, U1 prime, last one, and last one should come back here, because there is a loop. That is where it is coming. Finally, there is a loop. And then, so everybody gets how much time? Takes how much time? TL by WL, everybody. If it is at all possible to break this total job equally like this, then only I can talk like this. Again TL by WL, dot 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 dot. And how many delays I have? WL. Okay, so I give one delay here, D, and because how many nodes I have? WL number of nodes. So start with 0, U0 prime, in front of it you give one delay. U1 prime, in front of it you give one delay. U2 prime, in front of it you give. U3 prime, give one delay. Okay, and finally this UWL minus 1, this is actually UWL minus 1, that's total. So in front of it you give one delay. How you give the delay? By just retiming, because by retiming we know we can move some delay forward or backward. So by doing so you keep maintain, everybody gets one delay. Okay. Then according to me this is the best. It's because every edge has a delay. So the time of no two nodes will get added up, because critical path will be either time of this node or this node or this node or this node or this, whichever is maximum. But here all are same. So critical path will be TL by WL. That is new critical path. Okay, this is a new critical path. The times will not get added because they are separated by delay. So these are not delay free paths, they are not delay free edges. So I take individual times of each node, all are same. So critical this. Okay, and then another nice thing you see, I mean I am using only one delay per edge. I am not wasting any extra delay. Just minimum delay required to separate the two nodes is D. So that is what I am doing. So it's optimum use of the total available delays, and for the and under that per node I have TL by WL amount of time. So critical path is TL by WL. My claim is this is the best that can be done. Now you can say, why do you say so? Suppose I mean one of the nodes, maybe this one, the first one, instead of making it TL by WL I make it shorter, that is less than this time T0 prime less than this. Then you can say, look, I have made it less, so why you have to stick to TL by WL? I can, by designing these processors, I can make one of the nodes or few of the nodes shorter than TL by WL. But then if I make any one shorter, at least one of the other nodes or several of the other nodes will get thicker. Okay, so the time there will be more. Maybe here the time T2 prime may be more, or maybe T1 prime may be more. Now what is critical path? I have to take the maximum of the individual computation times here, because everybody has to finish the job. So in this case critical path increases. Okay, so the best that can be done is this. Okay, the best that can be done is this. So this is the figure of merit. It's called, this figure is called loop bound. This figure is called loop bound. Okay, that is total computation time of the loop TL divided by WL. What does it stand for? That is, this will give the best possible critical path, minimum possible critical path you can arrive at in the loop by retiming. You cannot go down below this. You cannot go below this. This is the best. And then suppose you have got many loops in the DFG. Then whatever is the highest loop bound is called iteration bound. Highest loop bound is called iteration bound. Okay, highest loop bound is called iteration bound. So for the entire DFG, that will be the best that can be done. Okay, for the entire DFG, that is the best that can be done. Okay. So this works like a figure of merit. So you have understood why we take this thing. I mean, what is the problem in this retiming of the loop? Now after this, so we have obtained this figure of merit for loop. We can take some examples. Okay, maybe I will take one or two examples after a while, and then we will see how to calculate the loop bound, iteration bound and all that. Iteration bound for the entire DFG is a figure of merit as far as loops are concerned. That if you only focus on the loops, the net critical path cannot be brought down below the this thing, iteration bound. Okay, this is for the loops. Our next topic is cut set retiming, which is a very important topic and very fascinating topic. It requires some intelligence also. Here, cut set retiming. This is a special way of doing retiming. Of course, we do not violate retiming theorem, because if you violate retiming theorem and do some arbitrary adjustment of delays, the new circuit will no longer be identical or equivalent to the original circuit, you are lost. So, we will not do that. But then you must have seen that we had lots of liberties in choosing the retiming values, only some inequalities were to be satisfied, but after that we had lots of liberties, lots of ways one can choose. A particular way, particular systematic way of choosing this is called cut set retiming, which is basically done by visual inspection of a given DFG, visual inspection of a given DFG, and then assigning certain retiming values. Okay, that is called cut set retiming. This requires a lot of intelligence. Okay, given a circuit, there is not a unique way of doing cut set retiming. It's up to your choice. You can choose a cut set to be this, you can choose a cut set to be that, so on and so forth. Okay, so in cut set retiming, what you do? You look at the entire DFG. Okay, you look at the entire DFG. By visual inspection, you cut it into two halves, separate it into two halves. Okay, one half has some nodes inside. Dot 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 dot. Maybe there is a source node S. I am considering single source. So, single source could be either on this side or this side. I am taking to be on this side. These nodes, they are internally connected. No node will be hanging separately. Okay, maybe this way, this connection, all this. But there are some nodes, they have their own connections, okay, and there are some nodes here, like that. Okay, same here. There may be some kind of internal connections. Arbitrarily I am drawing. There are some nodes here. All right. So, there will be edges, because after all the DFG is a connected graph. So, it is not that it is separated by two. So, from some nodes here there will be edges to some nodes on this side, dot dot dot. Okay. And from some nodes here there will be edges on the reverse side. They may have delays, may not have delay. So, I just remain general. So, I say that it may have a delay L1 times t, it may have L2 d dot dot dot, maybe total I have got LP. So, total p number of edges in this direction, LP number of d. So, all these delays L1, L2, LP, they are positive, unless non-negative, cannot be negative, either 0 or positive. Similarly, in the opposite direction, okay, in the opposite direction, we will have maybe R1d, R2d, R3d dot dot dot, or QD. There is Q number of paths in the opposite direction. This is the most general case. You may not have paths in both directions. Okay, you may have paths in one direction, but I am taking more general. And these nodes are all internally connected. This may have connection here, this may have connection, this may have connection here, like that. Nobody is hanging separately. This is a connected graph, and the source node maybe is connected to one node or 1 minute. Maybe here one node, it may be connected to other nodes and all those. Okay. Now, this is the structure. I just separated out one segment under this region, another segment, but actually this is just various nodes are there, they are connected between them like this, and one single source may be connected to one node here. We maybe have source may have connection to multiple nodes also, that is easy, that I will come to, but single source I have put it deliberately on this. Now, these edges, from left to right and right to left, they qualify to be a cut set if I remove them, and after removal of them the original DFG is separated into one full sub DFG where all the internal nodes are internally connected, nobody hanging separately, and another separate sub DFG, again all the nodes are internally connected and nobody separated out, nobody is hanging separately. Okay. So, then I indicate them by passing a dotted line through them, dotted line. So, whichever edges the dotted line cuts, those edges are part of the cut set. Like this dotted line goes through these. If you remove them, obviously I am left with this sector and the other sector, no connection between them, but this itself is a sub DFG by itself, internal nodes are connected, here also internal nodes are connected. So, I cut it into 2, not 3, not 4, only 2. Then this set of edges form a valid cut set, because just cutting them, I cut the given DFG into 2. So, first task will be to identify such cuts. Remember, there is nothing unique. One DFG, you can view it one way, you can take some of the edges to form a cut set, your friend can take some other edges to form a cut set, and you can go on doing cut set retiming again. Okay. Well, if some people are smart, they will arrive at the answer quickly, otherwise they will choose wrong cut sets or not as very useful cut sets and go on doing retiming. Okay. There lies the intelligence. So, in the next half, we will see how this can be used for doing retiming. Thank you very much.